Conference. Yesterday, Bela Balabash asked who is going to be the Erdős of the 21st century. I think there are a number of likely candidates here, but amongst the most likely, I think, is our next speaker. I picked up a book in the book display yesterday, and I turned to the index, and only about 150 entries. 14 of these mentioned the name Gowers. You know, the Gowers inner product, or the Gowers box space, or the Gowers triangle inequality, or the Gowers wolf theorem. I could use up most of the morning. Anyway, today he's going to talk to us about a couple of fairly famous problems of Erdős on arithmetic progressions, both of which are still open. Timothy Gowers.
Thank you very much. I sort of feel I immediately want to deny what has just been said, but okay. Well, as everybody else has said, it's a fantastic honor and privilege and pleasure to be at this conference. Okay, so I naively thought that this microphone worked, but it's got a green light in there, but I will try to stand near this one. I have slight regrets about Erdos because although I met him a few times, I never really had all that much to talk to him about because while he was still alive, I was mainly working on Banach spaces, and although he was interested in everything, that wasn't his sort of main interest. And by the time I started working on things that would have interested him, I think, quite a lot more, it was too late. But I nevertheless would like to talk about, what have I just done?
Just say no.
Nem? Does that mean no or does that mean yes? Sounds like no, but that's not a good guide, I think. But, okay. Well, it would be very strange to have a conference for the centenary of Erdos without mentioning the first problem here, which is perhaps his most famous problem, that if you've got a set of integers and the sum of the reciprocals of those integers diverges, then that set contains arbitrarily long arithmetic progressions. The second problem is not quite so well known, but is pretty well known. I know it as Erdős's discrepancy problem, and I'll explain why that's a good name for it in a minute. If you've got a sequence of plus or minus ones, what this says is that you can find an arithmetic progression of the form d, 2d, 3d up to md, such that if you sum along that arithmetic progression, you get modulus at least c, where c is some arbitrarily large constant that you can choose in advance. So I will come back to the second one. I'm going to start by talking about the first problem. But before I talk about either of them, I'd like just to mention that there is a third famous conjecture of Erdos that could be said to be a conjecture about arithmetic progressions, the conjecture about covering congruences. And so that says that for every m, you can find distinct moduli R1 up to Rk that are at least as big as m, and integers A1 up to Ak, such that every integer is congruent to Ri mod Ai, what the other way around? Ai mod Ri for some I. I'm sort of glad I didn't decide to talk about that because I learnt recently that it has been solved and it's going to be talked about, I believe, on Friday, though I think the timetable has been sort of changed here and there, but I think it's Friday, by Bob Huff. So that was a very exciting piece of news. But it also frees me of the need to talk about it had I decided to talk about it in the first place. Okay, so let's get back to the sum of reciprocals conjecture. First of all, why is it formulated the way it is? I think this is something that needs to be thought about a little bit. So let's define, given a set A, let's just define a density function to be the density of A in the first n integers. So delta A of n is the number of integers that belong to A in the first n integers divided by n. And although this isn't an exact equivalence, roughly speaking, the sum of reciprocals and conjecture tells us that if, sorry, I didn't actually say this here, but if A does not contain an arithmetic progression of length k, then this density function should decrease a little bit faster than log n. That's, as I say, it's not exactly equivalent, but if you can prove that, then almost certainly you've done the sum of reciprocals conjecture. In particular, if you could get a bound of n over log n squared for the density you need for all n, that would be sufficient, I think, a sort of exercise to prove that. Well, basically it follows from the fact that the sum of 1 over n log n squared converges. So why should we be interested in this conjecture? Well, there's a fairly natural reason, which was that a famous set for which the sum of the reciprocals diverges is a set of all primes, and this is a result that Erdős rediscovered at a very young age, as I'm sure most people here know. In fact, that, as I'm sure most people here know, applies to quite a lot of what I'll say, but I will make that apology just once. So, if one could prove this conjecture, one would have something that Erdős very much liked, which is you take a result that looks as though it's number theoretic or uses deep tools, and then you discover that some vast, purely combinatorial generalization of it is also true. And he had some beautiful examples like to do with numbers of points in circles and things like that. There were some very, very beautiful results of Erdos that took precisely this form. So that would be the big prize, except that unfortunately the prize has now been taken by Green. Well, not unfortunately, but unfortunately, if that's what your motivation was, that's been taken. We now know the Green-Tower theorem. We now know that the primes contain arbitrarily long arithmetic progressions, but not by purely combinatorial means. That uses very much, it uses facts about the primes that go well beyond the mere density of the primes. They go well beyond what you can get from the prime number theorem. So I think it is still the case, I don't think anyone here would dispute it, that it would still be very, very nice to prove the sum of reciprocals conjecture, even though we know that the primes contain arbitrarily long arithmetic progressions. I was actually, I talked at the 1999 Memorial Conference, and at that time I speculated about, some people may remember this, I speculated about when I thought that about the sort of difficulty of proving that there are arbitrarily long arithmetic progressions in the primes and proving the sum of reciprocals conjecture. And at the time I tentatively said that I thought that the primes conjecture would be solved in the foreseeable future, not sort of at any predictable time, but somehow it felt as though I could possibly hope to live to see the proof of that, and I wasn't so sure about the sum of reciprocals conjecture, and well, it's a small thing, but I've sort of been proved right. But if somebody were to prove the sum of reciprocals conjecture tomorrow, I think I'd then have to say, well, okay, I overestimated its difficulty, that's right. So, okay, so where have we got in our, we meaning the entire mathematical community, in our attempts to prove the sum of reciprocals conjecture? Well, if you reformulate it in terms of the density function, then an obvious first question is, does the density at least tend to 0 if A doesn't contain a progression of length k? And that was a more or less equally famous conjecture of Erdos and HUN-REN, and proved by Semerady in 1975, or at least the paper came out in 1975. So Semerady's theorem, from that we know that the density does have to tend to 0, but the proof didn't tell us, well, I think it is possible, if you're a logician or something, to extract some kind of bound from Semerady's proof. I've heard conflicting things about that, but at least now there are versions of Semerady's proof from which bounds can be extracted, but they don't get anywhere near 1 over log n. And in 1977, Furstenberg came up with another proof, which was also qualitative. Again, a very interesting paper of Terence Tao turned Furstenberg's argument into an argument that was, in principle, quantitative, but again with a sort of Ackermann-type bound or something like that. So again, it was not quantitative in quite the sense that I mean, or in the sense that would give one hope for the sum of reciprocals conjecture. So let me leave things there, and another thing to do if you want to look at the first question is to say, well, let's take the first non-trivial case. So progressions of length 2 are a trivial case. What about progressions of length 3? And here there's a very interesting story. The first progress towards any of these results at all was due to Roth. In 1953, he proved what is now sometimes tentatively known as Roth's theorem, but then you always have to say it's not Roth's theorem about Diophantine approximation. But anyway, Roth's theorem on arithmetic progressions, and he obtained a bound of constant over log n using Fourier analytic techniques. Roughly speaking, you find a Fourier expression for the number of progressions of length 3 in your set, and either that expression is quite small, in which case you're guaranteed a progression of length 3, or it's not small, in which case a fairly simple argument allows you to pass to an arithmetic progression of length roughly the square root of n, in which the density has gone up by a factor 1 plus delta, where delta was the original density. And if you iterate that argument, you eventually arrive at an arithmetic progression, but because you've had to take square roots quite a lot of times, roughly 1 over delta times, if you think about it carefully, you get a bound of constant over log n eventually. Another argument that was in a way similar, it again used Fourier analysis and again passed to subprogressions, but did so in a cleverer way. It considered bunches of Fourier coefficients all at once, due to Heath, Brown, and Semerady, gave a bound that was a power of 1 over log n for the density, a fairly small power, and Bourgain got that power to a half. And so that was Bourgain's result was a very nice result. The scheme of it was fairly similar. You do some Fourier analysis, and if the Fourier coefficients are small, you get your progression, and if they're big, you can pass to some substructure. But for him, the substructure wasn't an arithmetic progression of length the square root of n, but of something called a Bohr set, which looks a little bit like a projection of the intersection of a convex body with a lattice down into Z. If you do that, it enables you to carry out the argument rather more efficiently. And he got this bound of log n to the half. And for a long time, that looked like the furthest one could go by that sort of method. I think it's fair to say. I think many people, there's certainly reasons that it was hard to go beyond the power half. But then Bourgain surprised everybody by going beyond a half and getting 2/3 by doing a sort of refinement of the argument that had got a half. And I think equally surprising was that Tom Sanders then got from 2/3 to 3/4. Equally surprising because somehow you feel if Bourgain has squeezed all the juice out of something, there shouldn't be any more juice, but there was in this case. And then I had an amusing email exchange with Tom at around this time. I wrote to him and said, I hear about your 3/4 thing, that's very nice. And he said, well, actually, I'm not so interested in it anymore because he had just managed to get the power from 3/4 to 1. Unfortunately, with a log n to the 5 factor, so it's tantalizingly close to the logarithmic barrier that would enable one to get the sum of reciprocals conjecture. And actually, even if you manage to get a small constant times log n over log n, that would be enough to get the primes from the prime number theorem, because you can do the so-called W trick. You can pass to an arithmetic progression in which, by an arithmetic progression modulo some highly composite number, where the density of the primes goes up slightly from 1 over log n to log n over log n. So we're within log n to the 4 of one very interesting combinatorial proof, and within maybe log n to the 7 or something like that of another one. but perhaps, what is the actual truth of the matter? Is it maybe the barrier is in fact around 1 over log n, or slightly bigger than 1 over log n? So that's something that's worth thinking about. And there's been all sorts of evidence that's emerged over the last, well, since I gave the talk back in 1999, that I find quite suggestive, although not conclusive. So I've always been an optimist and always believed that the sum of reciprocal conjecture is true by miles. But I want to... so what do we have in the other direction? We have the very tantalizing situation that there's a quite simple argument of Berendt, very ingenious. I don't know how he thought of it at all, but once he thought of it, it's quite easy to follow. And it goes roughly like this. You're trying to find a set of integers without any progression of length 3. So let's first observe that if you take a sphere in R to the D, that doesn't contain any progression of length 3. So the next step, let's intersect that sphere with Z to the D. So we've got a discrete set that doesn't contain any progression of length 3. And for that to be interesting, you'd like it to have lots of points. To achieve that, you just use a simple averaging argument. There aren't very many sizes of vectors in Z to the D, and so by the pigeonhole principle, there must be a sphere that contains lots of points. And once you've got that, you just project your set, well, I say just, but this is where the expensive part of the argument comes, actually. You project your set down from D dimensions to 1 dimension. In order to do that, you have to leave a sort of gap in each dimension. So you can only fill up, roughly speaking, half of each dimension. So you lose a factor 2 to the D. So you want your dimension to be as small as possible, but on the other hand, you also want it to be as big as possible for other reasons. So you have to optimize D, and it turns out that root log n is roughly the optimal dimension. And if you chuck that in, I hope what I've written here reduces the whole thing to an exercise. The bound of e to the minus constant root log n comes out. And this is very interesting in a number of ways. One of the things that's particularly interesting about this is that it shows that the probabilistic method doesn't produce, or the obvious use of the probabilistic method doesn't produce the best bound. So the obvious use of the probabilistic method would be pick a random set, pick the probability so that the number of points is bigger than the number of progressions of length 3, chuck out a point from each progression of length 3. That gives a bound of 1 over root n, or something like that for the density. And this is e to the minus c root log n is much, much bigger than 1 over root n. In some audiences, I'd have to justify that statement. I think people here are used to dealing with those sorts of bounds, so I don't have to justify it. But so that means you can't somehow come up with an argument that proves that quasi-random sets are best, or something like that. And that is a huge part of the explanation, I think, of why it's so hard. But what about the log n barrier? So we've got we seem to have two barriers that are very hard to pass. Why would one believe that, I myself somehow believe a Berendt type bound is more likely to be the truth than a 1 over log n bound, but can I justify that? Well, there was a piece of evidence that for a long time seemed to suggest that maybe the 1 over log n barrier was sort of fairly fundamental, and that is that there is another version of the problem in f3 to the n, and the Roth argument, which involves passing to progressions of length square root of n, which is very expensive in the integers, turns out to be much less expensive in f3 to the n, because you can pass, instead of passing to progressions, you can pass to subspaces of codimension 1. So you're only losing a factor 3 each time instead of a factor square root n, or you're not, instead of taking the square root of what you had before. And so a very clean, essentially the same argument as Roth, but it works very much more cleanly, and you get a bound of constant over little n. That little n, of course, is log n, because it's log of 3 to the n, so it's the equivalent of log n for the integer problem. And the simplicity of that argument made it one of the very frustrating. Of course, you can't come to a conference about Erdős without being bombarded with very simple arguments that don't seem to be best possible and are extremely hard to improve, beautiful problems like that. And this was an example of that kind. But Michael Bateman and Nets Katz very recently did improve it by a factor n to the epsilon. So that's log n back in the integer world. So we've got a tiny power better than 1. So in this other context, the log n barrier has been breached. We've now got to log n, so log of the size of the set to a power that's bigger than 1. So somehow some sort of philosophical reason that it must be the same in the two contexts and the bound is sort of log n, that all fails. So that, I think, hugely weakens any argument that says that the log must be the right barrier for the integers. Of course, many people started to think, could we take Sanders's breakthrough and the Bateman-Katz breakthrough and combine the two and end up with, it's just the obvious thing to wonder. And unfortunately, there are very good reasons, it seems, that that's not a straightforward thing to do, that somehow even getting started seems to be impossible with that project. So for that reason, I would say it's not absolutely conclusive evidence that the 1 over log doesn't work, isn't the right bound for the integers, but somehow it suggests it quite strongly, I'd say. And if you combine it with another piece of evidence, then I think it really becomes, for me, very, very likely that the sum of reciprocals conjecture is true, at least for progressions of length 3. And that's a result of HUN and Skredoff, which Tom Sanders alluded to yesterday. You can think of finding progressions of length 3 as finding solutions of x plus y equals 2z. If instead you go for a few more variables, you go for x1 up to x5 added together equals 5y, then it turns out that a much better bound is true. This used some of the techniques that were introduced by Sanders. And in fact, something that's not exactly the Behrend bound, but it's of the sort of e to the minus power of log n type, so that would be good enough for most people, I think, is true for this more general problem. When I say more general, I don't really mean that. It's a different problem, but a special case of a more general problem. So we do have a Behrend bound for a closely related problem for which previously the best bounds were the same as best known bounds were roughly the same as for progressions of length 3. But again, that's not absolutely conclusive evidence, because there are many situations where if you take a convolution of 2 functions, it sort of smooths things out with a few little gaps, and if you take a convolution of 3 functions or more, it smooths them right out. So for Roth's theorem, you're looking at the convolution of the characteristic function of the set A you're interested in with itself. So that's just 2 functions, and you're interested in whether that intersects the dilation of A or has a non-zero inner product with a dilation. And somehow you can't quite escape the thought that maybe the gaps that you're allowed to have, just a few gaps in the convolution, I'm being a little imprecise here, of course, might just exactly coincide with where the set A is if the density is too small. One could go on and on speculating about this. I think, personally, I think, well, for a long time I thought that the Behrend bound was right for progressions of length 3 for sort of rather vague heuristic reasons that slightly resemble the more precise arguments that have now been produced. But because the precise arguments have been produced and do it for this problem and not for the problem, or don't easily do it for the problem with just 2 variables, that sort of slightly shakes my previous faith. But nevertheless, it's still, I think, on balance, I believe that log is a barrier waiting to be breached. What about progressions that are longer? So in general, if you want a progression of length k, then you get this rather small power of log n, minus 1 over 2 to the 2 to the k plus 9. And when you've got progressions of length 4, that's been improved. Green and Tau have got so again, so e to the minus c root log n is, if you take logs, you get root log n instead of log n, so it's definitely better than log n. And they've got a sort of Heath-Brown-Semerady type bound in a finite field model. So finite field model means something like f3 to the n, except that f3 to the n is not suitable for progressions of length 4. So it's, was it f5 to the n that's done, or is it, yeah. Or maybe it's fp to the n for general p, but 5 is the. So that's roughly where things stand. What Supposing somebody did manage to, which seems not inconceivable, perhaps I'll stick my neck out and say that if there's a 110th anniversary conference, there's a 50% chance that the log barrier for progressions of length 3 will have been breached. What about longer progressions? Well, there are by now quite a number of different tools for tackling longer progressions. I don't think in any of them it's clear that if somebody could prove a really good bound for progressions of length 3, then you could just turn a handle and sort of introduce all these extra tools and get longer progressions. I think that's not at all obvious. For me, I think what I would think would be the most likely possibility if the whole thing gets proved is that somebody comes up with a really quite different technique for proving progressions of length 3 that generalizes more straightforwardly to longer progressions than the current techniques do. But that, again, is being very speculative. And it'd be just very interesting to see what happens. Okay, so I think it's time to move on to the other problem, or I'll run out of time. So Erdős's discrepancy problem. Let me reformulate it slightly in a way that makes it clear why it's called a discrepancy problem, although that's fairly clear already. So let's, and also it's useful to have a bit of terminology. So we'll call an arithmetic progression homogeneous if it's of the special form D, 2D, 3D up to MD. And in general, if you've got if we color the integers from 1 to n with 2 colors, we'll call the discrepancy with respect to a set the difference between a number of, say, reds and a number of blues, and the discrepancy in general is the maximum of the discrepancies over all the homogeneous arithmetic progressions. And what we'd like to do then is minimize that maximum. So we'd like to choose a red-blue coloring that's as equal as possible a number of blues and reds inside any homogeneous arithmetic progression. The conjecture of Erdos is particularly annoying because it doesn't ask for any bound at all. It just asks to show that it tends to infinity. So one way to think about it is the contrapositive. If Erdős's conjecture is false, it means there's an absolutely miraculous coloring of the integers and some number like 1,000,000, such that whatever homogeneous arithmetic progression you choose, the number of reds minus the number of blues has modulus at most 1,000,000. And that would be a quite extraordinary object, such a coloring. We'll see some sort of moderately extraordinary objects in a moment, though. So again, the first thing one thinks of is let's just take a random coloring and see what happens. And of course, then even just the sum up to n is going to be, on average, round about the square root of n. So random is not too brilliant. Another thing one might think of is to take, I'm saying it now because I haven't mentioned it later on, is to take some well-known completely multiplicative function from number theory, such as the function lambda, which is -1 on all the primes and then is completely multiplicative. So its value at n is -1 to the number of prime factors of n, not counting with multiplicity. If you believe the Riemann hypothesis, then that also grows like square root of n. So that again, actually if you've got two completely different ideas that give square root of n, you might sort of think, well, perhaps that's actually the truth of the matter. But it turns out to be very, very far from the truth of the matter. There's a sequence where the discrepancy grows only logarithmically. And it's a very nice sequence. It works like this. We'll start with a sequence that's not a +-1 sequence. It's this one here, 1 - 1, 0, 1 - 1, 0. It is completely multiplicative. And that means that completely multiplicative just means that the value at AB is the value at A times the value at B. And you don't insist that A and B are co-prime. So because it's completely multiplicative, all you have to check to show that... wait a minute. No, sorry, I was about to say something false. But anyway, it's very easy to check that any progression, any homogeneous arithmetic progression, the discrepancy never gets more than 1. So if I just take a progression of common difference 1, then it goes 1, the sums go 1, 0, 0, 1, 0, 0. And if it happens to be a multiple of 3, then it's just 0 all the way. So either way, you can't possibly get more than 1. Now, a sort of slightly odd observation. If I then stretch this sequence out by a factor of 3, so 0, 0, 1, I just stick 2 noughts before each term of the previous sequence and write that out, then again, that's going to have discrepancy at most 1, and so on and so forth. If you add all those up, you turn out to get a completely multiplicative sequence of 1s and minus 1s. If you've got a completely multiplicative sequence of 1s and minus 1s, then in order to check what the discrepancy is with respect to homogeneous arithmetic progressions, you only have to look at the partial sums of that sequence, because any other homogeneous arithmetic progression, the values there are either the values that you get at 1, 2, 3, 4, or minus those values. So either way, you've got something that's more or less the same as the partial sums. So if you just add all these together, then each one is contributing, each of these sequences is contributing at most 1 to the discrepancy, or to the partial sums, let's say, and the number of sequences that you're considering up to n is at most log to the base 3 of n, and so we get this bound of log to the base 3. In fact, you can say a little bit more. Here's a picture of the sequence. I've just stretched and left little gaps to make it clear how what it looks like. So it turns out it's a simple exercise that the partial sum up to any given m is just the number of 1s in a ternary expansion of m. And so that again tells you immediately that it can't be bigger than log to the base 3 of m. You can actually improve on this very slightly, but I won't bother with that. There's a thing that gives you more like log to the base 9 of m rather than log to the base 3. But logarithmic growth is the smallest that's known. And so again, we've got a slightly annoying thing where there's a fairly simple construction that gives the best known bound. And worse still, you would have thought that if you can make the additional assumption that your sequence is completely multiplicative, then somehow techniques from number theory would come in and you'd be able to prove, at least then, that there's some lower bound that tends to infinity. But even that is not known. And Erdős asked that question as well. It's a very natural question to ask, given the examples that we have. Okay, so what is it that makes this question hard? Well, I've already just mentioned there's a theme, a little theme that's running through both problems, that the extremal examples are not random. So when that's the case, it just rules out quite a lot of ideas that one might have for getting started. This example, although it's not a plus minus 1 sequence, is extremely annoying. You might hope, very often, and this works for Semiramis' theorem or the Erdős-HUN-REN conjecture, very often it's extremely helpful to take a problem that's about sets and convert those sets into functions, perhaps taking the values in the closed interval 0, 1 or something like that. So you just think of your sets as characteristic functions, and then you just want to use, you want to generalize your statement about sets to something about functions, and then you can immediately bring in a lot of tools from analysis, such as Fourier analysis. So here one might like to argue that merely from the fact that the sequence is on average big, you get discrepancy tending to infinity. But this example just kills that hope immediately. On average, this sequence has modulus 2/3, but its discrepancy is bounded. So this makes it look as though the problem is somehow intrinsically combinatorial, which is, again, it rules out a whole lot of the initial techniques. One might think of, perhaps we can expand it in terms of some clever basis and do a clever averaging argument or whatever. And unfortunately, this example exists. And I think a third reason is that there are some very, very long sequences with very, very small discrepancy. Polymath 5, I should mention this. This was an online collaboration that started about 3.5 years ago to think about this problem. And a lot of what I'm going to say is insights that emerged from that discussion. We had a sort of principle that any paper that was written would be written under a pseudonym and names would not be mentioned. But since all the names are out there online, I thought for this talk it was a bit silly to pretend that everything was done sort of purely collectively, when in a few cases there was it was very definite who had some nice ideas. So I've taken this decision unilaterally. I hope I won't annoy anybody else by doing that. But the people I might annoy are the beneficiaries of this policy. So this, by the way, it's an unenlightening slide, but I just wanted to show you the beginning of a sequence that has discrepancy at most 2. So if you take any homogeneous progression and sum along it, it never goes above 2 or below -2. Actually, I lied. This is not the sequence. This is half the sequence, and there's the other half. There are actually online available much nicer displays of this sequence. So here, it's very, very hard. It's hard to tell what a homogeneous progression is around here because we haven't got the numbers there. But there's online, if you want to find this or information about it, if you just Google Polymath 5, then one of the top hits is a wiki that's got a lot of information. And in the wiki, there's a page called Experimental Evidence. And it displays this in a grid that has width 24, which turns out to be quite good. It sort of reveals a lot of the structure. The squares are colored, and they have numbers written inside them. So you can, it's not still quite hard to understand some things that you might like to understand, but it's much better than this. But I just felt I needed to prove that it really was true. Now, as Tom Sanders said yesterday, actually, in his talk, one thing that you often like to try to do with a problem is generalize it, because either it produces something false, which is quite interesting, it shows sort of, puts some restriction on what you can do, or it reduces somehow your options for tackling the problem. And reducing your options should be good news, because it means you don't spend lots of time thinking about things that aren't going to work. Or it can be good news. If you reduce your options to 0, it's bad news, but sometimes it just gives you a clue. So there are some obvious generalizations here. What about instead of real numbers of modulus 1, we take complex numbers of modulus 1? That turns out to produce another problem that's unsolved. And if you've done that, you might as well go even further and take unit vectors in a Hilbert space. I'll just say that for the unit vectors in a Hilbert space, the best known bound is more like root log n. And the reason for that is you can do the same sort of 1 minus 1 naught, 1 minus 1 naught, except that when you then fill in the 3 times that, you do it as multiples of an orthogonal basis vector, and then when you do 9, you do a third orthogonal basis vector, and so on, and then you can check that now when you add them up, the norms of the 1 contributions you're getting, you've got logarithmically many of them, and they're all orthogonal, so it's adding up to the square root of log n. The third generalization or variant is, it's not quite so obvious what I mean by it, so I should say a little bit about it. This was an idea of Gil-Kallai, which was to take non-zero elements, and then the idea is you'd like to prove that amongst the sums along homogeneous arithmetic progressions, you get all possible values mod p. So you pick an arbitrary p, and then you'd like to say, and so this is a generalization because instead of just looking at plus minus 1, you're now looking at all non-zero elements mod p. And if you can prove that you get all values mod p, that shows that in the case of plus minus 1, the discrepancy must be at least p over 2. So this would imply the discrepancy problem. Gill's hope was that the polynomial method might be applicable to this more general problem. I'll just throw that thought out. Another thing I'd like to mention is I put observation in inverted commas because for Terry it might have been an observation. I think for most people this would have been a theorem. So he showed that it's not quite, so it's certainly not the case that the discrepancy problem is equivalent to the discrepancy problem for completely multiplicative sequences. Well, I say that, maybe it is, but it doesn't appear to be. But it turns out that there is something that comes quite close to an equivalence, and this I think is really quite amazing. So it says, supposing you've got a counterexample to the Erdős discrepancy problem, then you can build something that's a little bit like a completely multiplicative counterexample, except that there are a couple of differences. One is its complex numbers, which is not a massive difference, I would say. But the other is that it's not that the discrepancy itself is bounded. It's more like the average discrepancy. So again, you only need to look at partial sums. So you look at the average or the square average of the first n partial sums, and that's bounded. So the discrepancy would be allowed to get big occasionally, as long as it's compensated for on average. So there's some, I mean, again, one might think if you can prove the complex, completely multiplicative version, then it's quite likely that you'd get some sort of average statement and not just very occasional bumps to the discrepancy. So I don't know, what should one's attitude to this be? Should it be, oh dear, that means that the completely multiplicative version is just as hard as the original version, or should it be the other way around, that the original version is maybe there's a sort of handle on it? I'm not quite sure which attitude to take. So that was one rather interesting thing that came out of Polymath 5. Another one was an observation of Moses Charikar, who was also here. I don't know whether he's in the room, but he's also at the conference, which showed that, contrary to what I said earlier, there is, in fact, an analytic approach to the Erdős discrepancy problem. This was a gorgeous idea that came from his knowledge of semi-definite programming, which many people here also know about. So, supposing we can find some coefficients with the following property, that they sum to 1, so we've got some CMDs. These indexes MD are going to be applying to homogeneous arithmetic progressions. So MD will correspond to the progression D, 2D up to MD. And we've got some other positive coefficients that add up to infinity, or non-negative coefficients that add to infinity. And we write down a quadratic form. And the quadratic form is you take the homogeneous arithmetic, you take sums corresponding to homogeneous arithmetic progressions, you square them, chuck the coefficient CMD in front, and then you subtract off a diagonal form with coefficients Bn. Supposing you could prove that a quadratic form of that form is positive definite or non-negative definite, then that would show, in particular, that immediately implies a positive answer to the Erdős discrepancy problem, because if we take all of the x's to be plus or minus 1, then that sum here is just the sum of the bn's, which is infinity. So that tells us that this sum here must be infinite, but because the CMDs add up to 1, the sums along the homogeneous arithmetic progressions must be unbounded. Otherwise, the sum couldn't possibly be infinite. So there's an immediate implication that way. Of course, you could write down lots of ridiculous things that imply the Erdős discrepancy problem. But there's reason to believe that this is true because there is a converse implication, which I haven't written down, that says that more or less that this statement is actually equivalent to the Hilbert spaces version of the conjecture. So it's a reasonable thing to write down, and it seems as though it implies the discrepancy conjecture. So here we have actually got something where once we've done this, once we've reformulated in this way, we're no longer assuming that the xd's are equal to plus or minus 1, so it becomes an analytic statement of the kind that we really wanted. So I've just said that. So another reason for this conjecture being useful is it opens up the possibility of some kind of computer-assisted, not a computer-assisted proof, but a computer-assisted discovery of proof. You might hope that you take some large n, you work out what the best possible coefficients are for that large n, stare at them very hard, and try to write down some formula that captures the experimental evidence and then prove that that works in general. This has been tried. Unfortunately, there seem to be sort of edge effects. If you just go up to n and drop, because there aren't that many homogeneous arithmetic progressions up to n, it seems that you get some very sort of interesting, suggestive-looking coefficients, but they're not quite suggestive enough that you can just say, I see what the formula is here. After that, you sort of start running out of CPU time, or whatever the right phrase is. So it hasn't been made to work, but I still feel as though one shouldn't abandon hope of some kind of way of thinking about it like that. But it also has a nice corollary that there exists a sequence, if this approach works, then there exists a sequence Bn of weights such that if you've got a sequence with this analytic property that the weighted sum of squares is infinity, then it's got unbounded discrepancy. So it's a very nice analytic statement. So a nice question is just to come up with some plausible idea for what those weights might be. It's quite easy to work out a few things about what they can't be. So for example, if you've got a positive proportion of their weights on integers that are not, or an unbounded portion of if the sum is unbounded on integers that are not multiples of 3, then you can just hit it with the 1 minus 1 naught, 1 minus 1 naught example again. And that sort of argument applies to all sets of integers of the form I am not a multiple of m. So that somehow seems to say that the weights must be concentrated on integers with lots of prime factors or something like that. There may be number theorists here who can come up with their favorite examples of systems of weights that are concentrated on numbers with lots of small prime factors. If so, I'd be very interested to hear about it. But so far we're at the stage where everything that we tried to write down sort of seems not to work. I should mention that, very briefly, that there are ways of, if you can reformulate this whole thing in terms of the rationals rather than the integers, and then then you can sort of make all the weights the same in some sense, or roughly. That's a rather vague remark. But I still like this question. Just find a system of weights for which it is not obviously false that that statement there is the case. And I'll finish. I was rather worried about the timing, but I seem to have miraculously arrived at the last slide at precisely the right moment. So here's one more analytic generalization. It's actually sort of reached, there's the philosophy behind it is somewhat similar to the philosophy of the previous one I've just talked about. Supposing it's the case that for any infinite matrix, there's no real matrix now, any infinite matrix with ones on the diagonal and every constant C, you can find a pair of homogeneous arithmetic progressions such that the sum of the matrix entries over the Cartesian product of those two homogeneous arithmetic progressions has modulus at least C. Again, that rather trivially implies a positive solution to the Erdős discrepancy problem, because this time you take your sequence epsilon 1, epsilon 2, epsilon 3 of plus or minus 1s, and you set aij to be epsilon I times epsilon j. And then this sum here over p and q is just the product of the sum of the epsilons over p with the sum of the epsilons over q, and so at least one of them must be at least the square root of c. So we recover the Erdős discrepancy problem. But again, this is a nice question because, once again, it's an analytic question. I don't need the aij's to be plus or minus 1. I just need them to be ones on the diagonal. And being ones on the diagonal, that's not a set with one element doesn't count as an unpleasant discrete problem. That also has some sort of dual formulation, and it's equivalent to a statement that one can write down about Hilbert spaces. I won't tell you what that is. I'll just say that it's a sort of sanity check. This one is also not obviously false, but it's turned out to be quite a big generalization of the Erdős discrepancy problem. And I think so it's another way of attacking it. So I think the situation with the problem now is it's as open as ever, but whereas at the beginning of 2010 it looked, there weren't any handles on it. Now at least we've got handles on it, approaches that one could hope would work. The approaches that I've just discussed, I think, are things that, they're not things that have been tried so hard that we now realize they're just as hard as the original problem. I definitely don't have that feeling about it. In fact, let me stick my neck out once more and say that I think there's a 50% chance that this problem will be solved in the next 10 years as well. And with that, I thank you very much, and I'll finish.
Well, thank you. Are there any questions Comments? Answers, perhaps?
That's a good, yes. So the question was, what's the lower bound? What was the lower bound in the Bateman-Katz f3 to the n, Meshulam, etc. problem? That's another, I feel Erdos would be smiling at us because it's another embarrassingly big gap between the best known upper bound and the best known lower bound. So the best known method of producing lower bounds is to take a very low dimensional, like sort of 10 or something, take a 10-dimensional example, do the best you can for that, and then just take Cartesian products. And if you do that, that gives you alpha to the n for some alpha, which is, in other words, a power bound of 3 to the n. So the gap is between a power and a power of the size of the set and a power of log of the size of the set, where the second power is just fractionally bigger than 1. So that's wide open. And actually getting a bound that beats all powers in the f3 to the n problem would be a fascinating thing to do. And actually that's another reason, I suppose, not to be completely sure that f3 to the n tells you what's going on in z to the n. In z, I mean. Yeah.
Any other questions or remarks? If not, thank you again. Coffee break until 25 to 11.